When a continuous material is struck at a single precise point, the physical reaction is immediate and chaotic. The material violently ripples, vibrating as the impact energy disperses through the medium. In physics and engineering, we use a mathematical tool called a Green's function to calculate exactly how a system responds to a localized input like this. Because of that physical reality, we are trained to visualize complex, oscillating waves the moment we hear the term Green's function. This split screen shows two completely different physical responses. On the left, a dynamic governing equation yields a vibrating wave. On the right, a static governing equation yields a perfectly smooth, motionless deflection well. Both of these distinct physical phenomena are calculated using Green's functions. The trap is confusing the mathematical tool with the physical state of the system. The mathematics define how to isolate a point response. The governing equation dictates whether that response propagates. We can prove this by isolating the spatial response from the spatiotemporal response. By looking at a stationary object before introducing time, we can see that the governing equation creates the waves, not the mathematical tool. A Green's function does not inherently wave. It is simply a mathematical formulation that defines how a system reacts to a fundamental, highly localized input. We can observe a system in static equilibrium. A massive weight rests on a thick steel beam, forcing it into a smooth, stationary curve. This translates static equilibrium into a 1D mathematical model, a continuous beam with a downward force vector at position xi. The static governing equation dictates structural stiffness equals the applied load. To model this precise point, the forcing function becomes a purely spatial Dirac delta, infinitely concentrated. Tracing the resulting deflection gives the static Green's function, g of x xi, mapping the spatial deformation from a unit load placed quietly at xi. In linear algebra, this static Green's function is the continuous, infinite degree of freedom equivalent to an inverse stiffness matrix, which calculates how a structure displaces under given forces. The structural displacement is largest directly underneath the load coordinate, and it decays smoothly as you move along the spatial coordinate x. Notice what is absent from this formulation. There is no time variable, t, and there is no temporal impulse, tau. A static response might feature sweeping curves or even reverse its sign to satisfy the physical supports at its boundaries. Those bends are strict spatial distribution necessities to maintain structural equilibrium. They are not waves. The static Green's function is strictly a spatial map of displacement. It completely lacks the mechanical properties required for wave propagation. We introduce time through a dynamic impact. A heavy hammer violently strikes a steel beam, replacing stationary bending with high-frequency mechanical vibration. Returning to our 1D beam schematic, the equation transforms to include mass, damping, and time derivatives, accounting for sudden material acceleration. Tracking changes over time means our point input must adapt. The forcing function expands into a double Dirac delta, an input isolated in a single spatial coordinate, chi-psi, and a single instant of time, tau. The mechanical output shifts entirely. Instead of a localized well, a wave propagates outward from the impact zone, bouncing off the rigid boundaries. This evolving time history output is the dynamic Green's function. In the static model, the input was a resting load. Here, the input is a concentrated impulse. The material exhibits reflections, interferences, and oscillations exclusively because the mass and temporal derivatives in the governing equation allow for wave dynamics to exist in the first place. The dynamic Green's function produces a rippling visual signature because the input injects a temporal impulse into a mathematical framework built to carry waves. This leaves an underlying physical question. Why does a mathematically simple, infinitely narrow point input trigger such complex, chaotic wave patterns? Here is the geometric profile of the Dirac delta function in space and time, a single, infinitely narrow spike. We analyze this by applying a Fourier transform, decomposing the signal into its constituent frequencies. Moving into the frequency and wave number domains reveals a mathematical truth. The infinitely sharp input spike translates into a perfectly flat, horizontal line spanning across all possible frequencies. Structurally, this broadband spectrum means the impulse doesn't excite just one localized behavior. The flat frequency band maps directly onto the material's distinct vibrational modes, overlaying everything from slow, primary bends to tight, high-frequency ripples. At the exact moment of the temporal impulse, tau, every single one of these distinct structural modes triggers simultaneously. The physical fallout of this simultaneous trigger happens chronologically. Lower frequency modes react immediately and travel slowly, while higher frequency modes propagate outward at entirely different speeds. As these modes travel at different velocities, the boundary conditions of the material force them to reflect back and crash into one another. The visible waviness of an impact is the chaotic superposition of these propagating and lagging sine waves stacking on top of each other. The complex rippling signature of a dynamic Green's function is simply the continuous material executing its entire vibrational catalog all at once. We can definitively separate the underlying mathematics from our visual assumptions using this comparative matrix. In the static column, we have a stiffness equation governed by a purely spatial input, resulting in a spatial function. The output geometry is a smooth, non-oscillating deflection curve. In the dynamic column, we have a wave equation, governed by a spatiotemporal input, resulting in a spatiotemporal function. The output geometry is a complex, vibrating wave pattern. The static case maps a stationary spatial spread. The dynamic case maps the time-evolving propagation of an impulse. Stripped of its physical context, the mathematical concept of a Green's function only asks one question: how does this specific system react to a fundamental point input? The mathematics of the point input remain constant. The wave is merely the physics of the continuum answering back.